Hello guys, I hope you are doing well. We are in the 8th episode of a Statistics for Machine Learning series, and we have just 2 more episodes to go. Today, we are going to talk about probability in machine learning. Let's start simple. When you flip a coin, you don't know the outcome, you just estimate it, right? We have a 50-50 chance of getting a head or a tail. Machine learning works the same way. Every prediction it makes carries uncertainty. And that uncertainty is what probability helps us describe and manage. Without probability, models would just make blind guesses. So how do we describe uncertainty mathematically? Let's start from the basics. In probability, a random variable is just something that takes on uncertain outcomes. For instance, the weather, your test score, or whether an email is a spam or not, they all carry a probability. This concept becomes the foundation for everything in ML, from logistic regression to neural networks. Now let's connect this to how models learn from data. Imagine you train a spam classifier. Instead of just saying spam, it might say spam equals 0.8, not spam equals 0.2. That's probability at work. It tells you how confident the model is. So this is why probabilistic thinking matters. You're not just guessing, you're reasoning with uncertainty. But how does a model calculate those probabilities? Let's look at a classic example. This is Bayes' theorem, the backbone of probabilistic reasoning. It says the probability of your email being a spam, given its words, depends on how likely those words appear in spam emails. This is a concept called conditional probability. Conditional probability is at the heart of how ML models update beliefs. And I would say, think of it like this. The probability that someone goes jogging, given it's sunny, is higher than if it's raining, right? So in ML, we use this logic all the time. For example, the probability someone clicks an ad, given they're interested in the fitness or not. Now let's connect this with another concept you have probably heard of, independence. When two things are independent, one doesn't affect the other. For example, flipping two coins. The first one doesn't influence the second one. But in real-world ML data, independence rarely holds. And that's why methods like naive Bayes fail when features are highly correlated, because it assumes independence that isn't really there. So far, we have seen how probability helps models make predictions. Now let's look at how it measures uncertainty. To measure uncertainty, we use probability distributions. Probability distributions are powerful tools. They tell us not just what the model predicts, but how confident it is. For instance, if two classes overlap, the model's confidence will drop, and that uncertainty can be modeled using probability distributions like Gaussian or Bernoulli. Now let's close everything by connecting them to a practical ML scenario. Imagine we have a logistic regression model. Logistic regression doesn't predict a label, it predicts a probability. For each input, it calculates the likelihood that the outcome belongs to a certain class. Then we set a threshold, say for example 0.5, to turn that probability into a final decision. For example, if it belongs to the spam class or it belongs to not spam class. That's how probability quietly powers one of the ML's most popular algorithms. So probability isn't a side topic, it's a language that lets ML models understand and quantify uncertainty. I hope this video helped you get a sense of how important probability is in machine learning models. In the next episode, we'll see how to evaluate models statistically. Because probability alone isn't enough, we also need to measure performance with confidence.